We are considering this function, and we found the numerators, the zeros of the numerator by setting each of these factors equal to 0. And the numerator is 0 when x is 0.75 or -1. And since the denominator isn't 0 at either of these x values, and you can check that out very easily, that means that the function has value 0 when x is -0.75 or -1. So if we're trying to graph this, we're safe in putting our x-intercepts at -0.75 and -1. Now, the denominator can be found very similarly to be 0, and it's very simple to do that, at x equals -1/2 and at -6. Now we want to talk about the effect of the zeros of the denominator on the graph. We also said that when x equals one of these numbers, of course, the value of y is undefined because you can't define division by 0. So we talk about what happens if x is near one of the zeros. For example, -6. If x is close to -6, then this is close to 0, which means it's very small, which means that the denominator is very small. Now, the question we ask is what happens if the denominator is small? And we found that most students were unable to grasp the implications of a small denominator. So we move to this sequence of calculations. 1,000 over 100, 1,000 over 10, 1,000 over 1. You see, we're dividing 1,000 by numbers that get smaller and smaller, and these numbers are rapidly approaching 0. They're never going to get there if we follow the pattern, but the pattern should be very clear. We're making the denominator 10 times smaller each step and asking what happens when we divide. Now, picture. If this rectangle here represents 1,000, then I can divide it into hundreds. And I can count 100, 200, 300, 400, 500, 600, 700, 900, 1,000. Okay, so I've got enough rectangles, small rectangles, representing 100 to total 1,000. So that 1,000 divided by 100 is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It takes 10 100s to make 1,000. I can count on my fingers. I can count by hundreds to 1,000. 100, 200, 300, 400, 500, 600, 700, 800, 900, 1,000. So 1,000 divided by 100 is 10. I'm not going to write that up here. You should be taking notes. Okay. Then I ask people to divide 1,000 by 10, not using a calculator. Totally unnecessary and ridiculous to use a calculator to do these calculations. I asked people if they could draw a picture of this, and they said, yeah, they could. You know, take a little while. You'd have to divide each of these little rectangles into 10 and then number them, and it would take a long time. Alternatively, as we did here, instead of counting to 1,000 by hundreds, we can count to 1,000 by tens. And I asked people to take 15 seconds, and I asked them to show me they were counting on their fingers, because the first time I asked, I don't think half the class even did it. They just sat there in the passive mode, which is not the way you want to act during class, but yeah, no offense taken here, but you're going to learn it by doing it. So I asked people to show me if they were counting on their fingers, and they go, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 10, 20, 110, 120, okay? And then I asked how far they got, and most of them got to 4 hands, which would be 40, because each set of hands is 10, or 5, which is 50. So they got halfway to 1,000, or nearly halfway to 1,000 in 15 seconds. So whereas this is just a couple of seconds of counting, this is about 15 or about maybe 30 seconds of counting, maybe 40 for most people. Doesn't take an exorbitantly long time. Now, you could count to 1,000 by ones. Everybody knows how to count by ones. I don't have to demonstrate that. Or count by point ones. Okay, how do you count by point ones? 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1. 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, 1.10, no, 2. Okay? And you know that. Okay. So that would be feasible, but it took all that time just to get up to 2, and we got to get all the way to 1,000. So it would take probably a number of hours to do this. To do this one or this one would take correspondingly longer. Each one would take 10 times as long as the one before it because of the way you count. For example, by 0.001, 0.001, 0.002, 0.003, 0.004, 0.005, 0.006, 0.0007, 0.008, 0.0009. It's not 0.0010, it's 0.01. And then you do this again, 0.011, 0.012, 0.013, 0.014, 0.015, 0.016, 0.017, 0.018, 0.019, 0.020. So we're up to 0.02 after 2 hands. Well, it's going to take us quite a while to get up to 1, and then we're going to have to do that 1,000 times. So this is going to take a long time. From this, we grasp the meaning of what it means to divide. Okay? Now, the meaning of division is not punch this button and get this result. The meaning of divide is how many of these does it take to make this? And if this is really small, it takes really a lot of them to make this. And the smaller this gets, the more this requires. So as this number approaches 0, there's no limit to how big or how many it's going to take to make up this. There's no limit to how close this number can get to 0, so there's no limit to how big the result can get, which means that the result approaches infinity. The result is unbounded. There's no upper bound on how many times this number can go into this if this number approaches 0. Okay, well, with that in mind, we see that x plus 6, if x is close to negative 6, the closer x gets to negative 6, the closer this gets to 0. And by letting this get close enough to by letting x get close enough to negative 6, we can make this as close to 0 as we need. And we can make it close enough to 0 to make this whole denominator as close to 0 as we need. Which means that this denominator can go into this numerator as many times as we might wish. And there's no limit to how many times the denominator will go into the numerator as x approaches negative 6. So that what we get is results for y as x approaches negative 6 that exceed all bounds, that approach infinity, or maybe negative infinity, because whether it's a positive infinity or negative. If the numerator was negative, then you'd be always getting negative results. And your result would be approaching negative infinity. We'll see a little bit more about that. But that's an essential property of rational functions. When your denominator approaches 0, unless your numerator also approaches 0, your result approaches infinity. And if your denominator is 0, then in any case, even if the numerator is also 0, you can't, 0 over 0 is not a defined operation, so that your y value isn't even defined when the denominator is 0. One other comment on this kind of a rational function. And a rational function is just a polynomial divided by a polynomial. Now we can see that this is a polynomial because, of course, we can multiply it out. And we know we're going to get a quadratic, and I think I multiplied it out correctly here, but you can check me on that. I only made one try and did it in my head. So multiply these together, we get this. If you have a rational function that looks like this, it's going to be hard to find the zeros. Of course, you can go to the quadratic formula and stuff, but if you have a rational function, the first thing you're going to try to do is put it into factored form, because in factored form it's very easy to find the zeros and very easy to see what's going on. This is the form in which it's easy to analyze a function like this.